Hello students, let us start the session with one valuable thought. Once you replace negative thoughts with positive ones, you will start having positive results. Students, in this session I am going to discuss thermodynamics part 5. That is, I am going to talk about Hess's law of heat summation, lattice energy, Born-Haber cycle for determining lattice enthalpy, and various statements of second law of thermodynamics. Let us see one by one. Now, starting with the first one, that is Hess law of constant heat summation. This law states that the enthalpy change of a reaction either at constant volume or at constant pressure is the same, whether it takes place in a single step or in multiple steps, provided the initial and final states are same. Once again, I repeat this law. The enthalpy change of a reaction either at constant volume or constant pressure is same, whether it takes place in a single step or multiple step. The enthalpy change, that is del H for the chemical reaction, is same whether it takes place single step or multiple steps. Consider a chemical reaction A gives B whose enthalpy change is delta HR. So this reaction takes place in single step. Okay, assume this reaction takes place in 3 steps, that is A gives X, then this X gives Y, finally this Y gives the product B. Okay, the same reaction takes place in 3 steps. Now delta H1, delta H2 and delta H3 are the enthalpy change of these 3 steps respectively. As per the Hess law, whether the reaction takes place in single step or in several steps, the enthalpy change is same. Okay, so as per this law, delta HR is equal to delta H1 plus delta H2 plus delta H3. So this is Hess law of constant heat summation. Now we are going to see the application of Hess law. Hess law can be applied to calculate enthalpies of reaction that are difficult to measure. For example, it is very difficult to measure the heat of combustion of graphite to give pure CO, that is carbon monoxide. However, the enthalpy for the oxidation of graphite to CO2 and the enthalpy for the oxidation of carbon monoxide to carbon dioxide can easily measured. For this conversion, the heat of combustion values, that is del H1 and del H3 values are minus 393.5 kilojoule and minus 283.5 kilojoule respectively. From this data, the enthalpy of combustion of graphite to CO can be calculated by applying Hess's law. So according to Hess law, del H1 is equal to del H2 plus del H3. Here del H2 is the enthalpy of combustion of graphite to CO. Therefore, del H2 is equal to del H1 minus del H3. If we substituting the values of del H1 and del H3, we can get the del H2 value, that is enthalpy of combustion of graphite to CO is minus 110.5 kilojoule. So using Hess's law, we can calculate the enthalpies of reaction that are very difficult to measure. Now we are going to see the next topic, lattice energy. So what is lattice energy or lattice enthalpy? Well, here is 1 mole of a crystalline ionic lattice, and the energy required to remove each of these ions out from the lattice, turn them into a gas and space them infinitely is the lattice energy or lattice enthalpy. Here is the definition. The lattice energy is defined as the amount of energy required to completely remove the constituent ions from its crystal lattice to an infinite distance. See the equation. From this equation, it is clear that 788 kilojoule of energy is required to separate the Na plus ions and Cl minus ions from 1 mole of NaCl. Now, Born-Haber cycle. Born-Haber cycle is primarily used in calculating lattice energy, which cannot be measured directly. The Born-Haber cycle applies Hess's law to calculate the lattice enthalpy. For example, consider the formation of simple ionic solids such as alkali metal halide MX. The following steps are considered. This is the direct formation of MX by a single step. The enthalpy change for this reaction is defined as the enthalpy of formation del HF. This reaction also involves 5 sequence of steps. First, solid metal is changed into gaseous metal atom, and the enthalpy of this step is equal to enthalpy of sublimation, that is del H1. Then the atomization of halogen by dissociation takes place, and the enthalpy of this step is equal to del H2. Then gaseous metal atoms are ionized to form metal plus 1 ion, and the enthalpy change for this reaction is del H3. The electron affinity for the conversion of atomic halogen to halide ion, that is X2 X minus, is del H4. Finally, the lattice enthalpy for the formation of solid MX from M plus and X minus ions is U. So here U is the lattice energy or lattice enthalpy. Now, according to Hess's law of heat summation, del HF is equal to del H1 plus del H2 plus del H3 plus del H4 plus U. From this formula, we can easily find the lattice enthalpy for the formation of solid MX U. Now, let me explain you with the help of one example. Born-Haber cycle for determining the lattice enthalpy of NaCl. NaCl means sodium chloride. The formation of NaCl can be considered in 5 steps. Now, this is the direct formation of NaCl, that is sodium chloride, by single step. The enthalpy change for this reaction is del HF, and it is equal to minus 411.3 kilojoule per mole. The other route involves a sequence of steps. First, solid sodium is changed into gaseous sodium atoms. The enthalpy of atomization of sodium, that is del H1, is equal to the enthalpy of sublimation, and it is equal to plus 108.7 kilojoule per mole. Then the atomization of chlorine takes place. It requires plus 122 kilojoule per mole. Then gaseous sodium atoms are ionized to form sodium plus 1 ions. This requires plus 495 kilojoule per mole of ionization enthalpy. The following step, changing chlorine atoms into chloride ion, is exothermic. The electron affinity energy released is minus 349 kilojoule per mole. Finally, gaseous Na plus ions and Cl minus ions are combined to form solid sodium chloride, that is NaCl. This lattice energy for the formation of NaCl is taken as U. According to Hess's law of heat of summation, del HF is equal to del H1 plus del H2 plus del H3 plus del H4 plus U. Now we have to calculate U, that is lattice energy or lattice enthalpy of sodium chloride, that is U is equal to delta HF minus of delta H1 plus delta H2 plus delta H3 plus delta H4. So on substituting these enthalpy values, we can get the lattice enthalpy of minus 788 kilojoule per mole. So here this negative sign indicates that the energy is released. The energy is released when the formation of sodium chloride. A large negative value for the enthalpy of formation indicates that the compound is very stable compared to its element. The compound is very stable compared to its element. So this is the Born-Haber cycle, and it is useful in calculating overall energy changes during the formation of ionic compounds. Now we are going to see second law of thermodynamics. We know from the first law of thermodynamics, the energy of the universe is conserved. Now, the most important question is, for what purpose is this law used? One of the main uses of the second law of thermodynamics is determine whether a process is spontaneous or not. The main use of second law of thermodynamics is to determine whether a process is spontaneous or not. Let us consider one example. A glass of hot tea over time loses heat energy to the surroundings and becomes cold spontaneously, which means without any external aid. But what about the opposite process? Will that happen spontaneously without any external aid? From your own experience, you know this will not happen. So, this process is not spontaneous. However, according to the rules of energy conservation or the first law of thermodynamics, even the reverse process is possible because in both states the energy is the same. So, what is missing here? There must be one more law which governs the direction of a process, and that law is second law of thermodynamics. Now, we will review the second law of thermodynamics. Here are the two standard definitions of the second law. One is Kelvin Blanc statement and another one is Clausius statement. One is Kelvin Blanc statement and another one is Clausius statement. We will see one by one. Now, what is Kelvin Planck statement? It is impossible by any thermodynamic process which results slowly in the removal of heat from a heat reservoir and convert it entirely into work. It means that it is not possible to get continuous supply of work from a body by cooling it to a temperature lower than that of the surroundings. The second law of thermodynamics explains why even an ideal frictionless engine cannot convert 100% of its input heat into work. So the second law of thermodynamics comes and says, no, dude, you cannot make an engine with 100% efficiency. That is not possible. Okay. Now, the efficiency of any heat engine is equal to work performed divided by heat absorbed. Efficiency of any heat engine is equal to work performed divided by heat absorbed, and the efficiency percentage is equal to Th minus Tc divided by Th into 100. Here Tc and Th are the temperature of cold reservoir and hot reservoir respectively. So the efficiency of a machine is always less than 1. Let me explain with one example. Suppose if an automobile engine burns petrol at a temperature of 816, that is 816 degrees Celsius, and if the surrounding temperature is 21 degrees Celsius, what will be the maximum efficiency for this? Here Th, that is temperature of hot reservoir, is 816 degrees Celsius, and Tc, that is temperature of cold reservoir, is 21 degrees Celsius. By converting these temperature in degrees Celsius into Kelvin, we get 1089 and 294 Kelvin respectively. Now, what is the formula for percentage efficiency? Yes, percentage efficiency is equal to Th minus Tc divided by Th into 100. So by substituting these values, we can get the percentage efficiency is 73%. So Kelvin Bloch statement suggests that no heat engine can convert whole of the heat energy supplied to it into useful work. Now the next statement, what is Clausius statement? It is impossible to transfer heat from cold reservoir to a hot reservoir without doing some work. Very important thing is without doing some work. It means that by itself a heat cannot flow from a body at lower temperature to body at higher temperature. So this is the Clausius statement. Now we are going to see entropy statement. So what is entropy? Entropy is related to the disorderness of a system or randomness of a system. So entropy is a measure of disorderness of a system or randomness of a system. So the entropy change ds is defined as the ratio of heat change, that is dq, to the temperature for the reversible process. So the entropy change is defined as the ratio of heat change to the temperature for the reversible process. So the nature says, or nature seems to be working in a way that no matter what happens, the entropy of the whole universe should increase in that process. Now the SI unit of entropy is Joule Kelvin inverse, that is JK inverse. Now, the second law of thermodynamics can be expressed in terms of entropy, that is, the entropy of an isolated system increases during a spontaneous process. The entropy of an isolated system increases during a spontaneous process. Otherwise, the statement also known as a process accompanied by an increase in entropy tends to be spontaneous. A process accompanied by increase in entropy tends to be spontaneous. So for an reversible process, total entropy change is greater than 0. That is, delta S total is greater than 0. Already we know that delta S total is greater than delta S system plus delta S surrounding. Here delta S is nothing but delta S universe. Delta S total is nothing but delta S universe. So delta S universe is greater than delta S system plus delta S surrounding, that is that is a entropy change of universe is greater than the entropy change of system and surrounding for an irreversible process. But for a reversible process, delta S system is equal to minus of delta S surrounding. So the delta S universe, that is entropy change of universe, is equal to 0 for a reversible process. Now we are going to see what is standard entropy change for a chemical reaction and formation of compound. Entropy, we already know that is measure of randomness. But what is standard entropy? The absolute entropy of a substance at 298 Kelvin and 1 bar pressure is called the standard entropy, and it is denoted by S0. The absolute entropy of a substance at 298 Kelvin and 1 bar pressure is called standard entropy. So this is the formula for standard entropy change for a chemical reaction. Delta S0 R is equal to summation of standard entropy of products minus summation of standard entropy of reactants. Once again I repeat the formula. Delta S0 R is equal to summation of standard entropy of products minus summation of standard entropy of reactants. Now standard entropy of formation is defined as entropy of formation of 1 mole of compound from the elements under standard condition. When there is a change of state from solid to liquid, that is melting, liquid to vapor, that is evaporation, or solid to vapor, that is sublimation, there is a change in entropy. The entropy of fusion, that is delta S fusion, is equal to the ratio of molar heat of fusion to the melting point. That is, what is molar heat of fusion? Delta H fusion to the melting point, that is TF. The entropy of vaporization, that is delta S vaporization, is equal to ratio of molar heat of vaporization to the boiling point. So here delta HV divided by TB. Here TB is the boiling point. Then the entropy of transition, that is delta ST, is defined as the ratio of molar heat of transition to the transition temperature, that is delta HT divided by TT. So what is transition? A conversion of one allotropic form into another allotropic form is called transition. So in this session we saw the Hess law of constant heat summation, lattice energy, Born-Haber cycle to determine the lattice energy, and the various statements of second law of thermodynamics like Kelvin-Planck statement, Clausius statement, entropy statement. Thank you.